A chemical equation must be balanced. Okay, what do we mean when we say that an chemical equation is balanced? That means that there should be equal numbers of each kind of atom on both sides of the arrow. So in other words, before and after the change, no atom should disappear, and you shouldn't be making any new atoms. Okay, so remember, all we're saying is at the atomic level, when you have a chemical reactions, you just have a rearrangement of the way the atoms are bonded to one another. Okay, so anyway, if you balance a chemical equation, okay, you have to make sure that uh, the, you have equal numbers of each kind of atom on both sides of the arrow. And the way you count the number of atoms, okay, involved in the reaction in your chemical equation is just multiplying the subscript for that atom by the coefficient of the compound or element that that atom is found in. Okay, so for example, let's verify that chlorine is actually balanced here. How many chlorine atoms are shown on the left side? Okay, chlorine right here is found in HCl. The subscript of chlorine is 1. The coefficient of the substance where chlorine is found is 2. Chlorine is found in HCl. So 2 times 1, so your chlorine on the left is 2 times 1. You have 2 chlorine atoms being shown on the left side. On the right side, you find your chlorine in calcium chloride. The subscript is 2. And the coefficient of calcium chloride is 1, so 2 times 1 is also 2. So you can verify that chlorine is balanced in this equation. So you can verify this for calcium, oxygen, carbon, and hydrogen. Okay? And if that's true for all of them, all the elements that are involved in this reaction, the atoms are balanced on both sides of the arrow, then you say that your chemical equation is balanced. Now, there isn't a unique way to balance a chemical equation. Okay? The coefficients needed to balance a chemical equation is not unique. So, for example, let's look at this example that we had again. The coefficients are, remember, 1, 1, 2, 1, 1, 1. Well, what happens if I change my coefficient of HCl to 6? Well, from 2 to 6, all I did was multiply that by 3. So to maintain the equation's balance, okay, I can just multiply all my coefficients by 3. So I can have 3 calcium carbonate, solid, plus 2 times 3, 6, 6 HCl aqueous. 1 times 3 is 3, 3 calcium chloride, aqueous. Plus 1 times 3 is 3, 3H2O liquid, plus, and then coefficient of CO2 is 1 times 3, 3CO2 gas. This is still a balanced equation. It just doesn't have the smallest possible set of whole numbers, but it is still a balanced equation. There's nothing wrong with it, okay? Although it is customary when balancing equation to use the smallest possible set of whole numbers. It's not necessary, it's not wrong to use other coefficients that are not the smallest possible coefficients. Okay, so how can we tell if we have the smallest set of whole number coefficients? Well, if one of those coefficients happens to be 1 and they're all whole numbers, then you've already got the smallest set of whole numbers coefficients. If not, if the smallest coefficient is now 1, then simply divide all those coefficients by the smallest of them, and then if we end up with whole numbers, then you already had the smallest whole number coefficients. Let's look at an example here. Which of the following, let's say you have these sets of coefficients, which of these can still be reduced to a set of smaller whole numbers? Well, let's look at A. The smallest here is already a 1, and that's already as small as can be. Okay, now the smallest is not 1, so what you can try to do is divide by the smallest number. So 5 over 2, 2 over 2, 3 over 2, 4 over 2. So that gives you 2.5, 1, 1.5, and 2. Well, now you don't have whole numbers anymore, so that means this is as small as can be. Okay, this cannot be reduced. This cannot be reduced. So obviously the answer to this question must be C. In fact, what happens if you have 3, 6, and 6? You divide by the smallest of these, which is 3, divided by 3, you can get 3 divided by 3 is 1, 6 divided by 3 is 2, 6 divided by 3 is 2. So you can reduce 3, 6, and 6 to 1, 2, and 2. Now, actually, you can even use fractional coefficients, okay? But just be alert to the fact that you can't have half a molecule. So when you have fractional coefficients, interpret that as a fraction of a group count, okay? A fraction of a mole, okay? So when you see 1/2 CO2 in your chemical equation, don't interpret it as involving half a molecule of CO2, but interpret it as half of a mole of CO2 molecules. If you recall, a mole is 602 billion trillion things, okay? So if you want to change your fractional coefficients to a whole number, all you have to do is simply multiply them by the least common multiple of the denominators, okay? If you really want small whole numbers. So for example, let's look at this balance equation right here. You can see, verify that this is balanced. Our nitrogen on the left, you have 1/2 times 2, that's 1. Nitrogen on the right is just 1 times 1. Okay, your hydrogen on the left is 3/2 times 2, which is 3, and your hydrogen on the right is 1 times 3, which is also 3. So that's a balanced chemical equation using fractional coefficients. It doesn't mean that half a molecule of N2 will react with 3/2 of a molecule of H2. There's no such thing as a half a molecule. What this means is if you have half a mole of N2, it will react with 3/2 of a mole of H2 to give you a mole of NH3. So if you want to change these to whole numbers, all you have to do is you look at your fractional coefficients, 1/2, 3/2, and then 1 is, of course, 2 over 2. So all your denominator, the least common multiple of your denominator would be 2. So multiply everything by 2. So now you have 2 times 1/2 is 1. 2 times 3/2 is 3. 2 times 2/2 is 2. So you can rewrite this. You can say, if I want to use the smallest whole numbers, that would be N2 plus 3H2 yields 2NH3. And like I said, there's nothing wrong with not using the smallest possible set of whole numbers. Now, on exams, sometimes questions are not worded very carefully. Okay? If the question asks, what should be the coefficient of this, technically, it can be anything, right? But usually what that means is if you were to have the smallest possible set of whole number coefficients. Okay? Sometimes that phrase is left out. Just be alert to that.